Now, if we have a 10 square millimeter cross-sectional area, that would be the cross-sectional area of the tube. This one I think is actually about 7 square centimeters, but 10 is an easier number to work with, so we'll use that. And a pressure of 120 kilopascals, so we have 120 kilopascals in the bottle, and that's supporting water column 2 meters high. Okay, what's the force on the base of the tube? Okay, well, the force on the base of the tube from the pressure is the pressure times the area of the 120 kilopascal, because that's what you have inside the bottle at the base of the tube, multiplied by the area 10 square millimeters. 10 square millimeters is 10 times 0.001 meters, quantity squared. 120 kilopascals, 120,000 newtons per square meter. So now we have meters squared, and we work out the numbers, and we get 1.2 newtons, because the meter squared here will be divided by the meter squared here, leaving us newtons. So we have 1.2 newtons of force acting upward on that water column. Now, the next question is, how much force on the top of the tube? We have 1.2 newtons on the bottom. We have atmosphere pushing down on the top. Well, the atmospheric pressure is 100,000 pascals, and the same type of calculation that I didn't repeat is going to give you 1.0 newtons, which you should confirm. So what do we have? We have the water in the tube. What are the forces on the water in the tube? We have 1.2 newtons up, 1.0 newtons down, and mg, the weight of the water acting down. What's the weight of the water? Well, take the volume of the water in the tube and multiply by the density of water. Volume of water in the tube is 10 square millimeters, the cross-sectional area, multiplied by the height, which is 2 meters, and that's going to be 2 times 10 to the negative 5th cubic meters, 4 zeros and a 2. Multiplying this by the density of water, which is 1,000 kilograms per cubic meter, we're going to get 0.02. You're going to move the decimal over 3 places when we multiply by 1,000, etc. So we get 0.02 kilograms, and multiplying that by the acceleration of gravity, we get a weight of 0.2 newtons. So now we have 1.2 newtons up, 1.0 newtons down, and mg, which is 0.2 newtons down. Well, the ups total 1.2, the downs 1.0 and 0.2 total 1.2, so we conclude that the water in the tube is in equilibrium. Now, of course, we already knew that, but this is a nice consistency check.